300 feet beneath the French-Swiss border, a machine built to test the laws of physics may have uncovered something no one expected. There was no explosion, no warning siren, no flashing lights, just a handful of numbers that refused to obey the universe's most trusted equations. For more than 50 years, the Standard Model has been the greatest success in modern science. It predicted particles decades before they were discovered. It explained why atoms exist, why stars shine, and why matter itself holds together with astonishing precision. Then, CERN looked deeper than humanity ever had. What emerged wasn't a single strange result. It was a pattern. Beauty quarks behaving unexpectedly, muons spinning in ways scientists are still trying to explain. A W boson whose measured mass sparked one of the biggest debates in modern particle physics. Different experiments, different teams. The same unsettling question. What if these aren't isolated anomalies? What if they're the first hints that our picture of reality is incomplete? If you're fascinated by the biggest mysteries in science, subscribe and join us on this journey. Your support helps us explore the frontiers of human knowledge, one discovery at a time. Because by the end of this story, you'll understand why a growing collection of unexplained measurements has some physicists asking whether we've reached the edge of the Standard Model, and whether the next discovery could change the way we understand the universe itself. Prepare for a journey into the hidden architecture of reality, where every answer reveals an even deeper mystery. We begin. There is a place beneath the ground where the laws of nature bend. Not metaphorically, not poetically. Literally, physically, the rules that govern every atom in your body, every star in the sky, every planet spinning through the dark, are pushed to their absolute limits in a tunnel buried 300 feet below the French-Swiss border near Geneva, Switzerland. That tunnel is circular. It stretches 17 miles around, wide enough that you could drop the entire island of Manhattan inside the loop and still have room. The walls are lined with superconducting magnets, cooled to negative 456 degrees Fahrenheit. That is colder than the surface of Pluto. Colder than most of the known universe. Inside the tunnel, a vacuum has been created so empty that it contains less air than the surface of the moon. This is the Large Hadron Collider, and it is the most powerful machine human beings have ever built. Here is what it does. Scientists take protons particles so small that billions of them could sit side by side across the width of a single human hair, and they fire them in two beams. Travelling in opposite directions around that 17-mile ring, they accelerate those beams until the protons are moving at 99.999% of the speed of light. At that speed, a single proton completes 11,000 full laps around the ring every single second. 11,000. In 1 second. Then, at 4 specific points along the ring, the beams are made to cross. The protons collide. What happens at the moment of collision is difficult to describe using the language of everyday life, because nothing in everyday life comes close to it. The temperature at the collision point reaches several trillion degrees, roughly 100,000 times hotter than the centre of the sun. For one tiny, almost unmeasurably brief instant. Matter as we know it dissolves completely. The protons don't just break apart, they melt. The quarks and gluons inside them, the fundamental particles that make up all visible matter, move freely, unchained, the way they did in the very first fraction of a second after the Big Bang. Then the energy converts into new particles. Particles that have not existed naturally anywhere in the universe for nearly 14 billion years blink into existence, live for a fraction of a trillionth of a second, and then fall apart. And in the way they fall apart in the specific pattern of their decay, the secrets of reality come spilling out. The machine runs approximately 40 million collisions every second. 40 million. Surrounding each of the 4 collision points are detector structures so large they fill underground caverns the size of cathedrals, so heavy they outweigh the Eiffel Tower, so precise they can measure the path of a particle moving at near light speed to within a millionth of an inch. The data produced by these detectors in a single year would fill more than 1 million laptop hard drives. Scientists spend years, sometimes careers, sorting through it. They are looking for anything that should not be there. To understand why that search matters, you need to understand what each particle carries with it as it flies through those detectors. Every particle has what physicists call a fingerprint, the specific way it decays, the angle it travels, the energy it releases, the particles it transforms into. These fingerprints were predicted by the equations of modern physics decades before scientists had machines powerful enough to check them. And for decades, every fingerprint matched the prediction perfectly. The Large Hadron Collider changed the nature of that matching. Previous machines could produce rare particles, but not in large enough numbers to run statistically meaningful tests. The LHC produces them in the hundreds of thousands, sometimes millions. That level of statistical power means that when a fingerprint doesn't match, you can say with real confidence, this is not noise. This is not a measuring error. This is a signal. And signals, in physics, have causes. The detectors that record these signals are engineering achievements almost as remarkable as the accelerator itself. The largest of them is called Atlas. It is 46 meters long and 25 meters high, roughly the size of a 7-story building, and it sits in a cavern carved out of solid rock deep underground. Every component was built on the surface and lowered down in pieces. It took years to assemble. Similar in design and purpose, the CMS detector weighs 15,000 tons and contains the most powerful superconducting solenoid magnet ever built. Then there is LHCb, the Large Hadron Collider beauty experiment. Unlike Atlas and CMS, which surround the collision point on all sides like a sphere, LHCb extends in one direction like a telescope, positioned to catch a very specific type of particle that tends to shoot forward at shallow angles along the beamline. That particle is called the beauty quark, and the story of what LHCb found when it measured the beauty quark, measured it across hundreds of millions of decays, is where everything in this story begins to change. But before we can feel the weight of what was found, we need to understand the framework those findings are contradicting. Because the contradiction is not small. It is not a rounding error. It is not a slightly off calibration. It is a challenge to the most successful and most precisely tested scientific theory ever constructed, a theory that has predicted the behaviour of matter and energy with extraordinary accuracy for 50 years, and that now, quietly, in numbers too stubborn to be dismissed, is showing its first real cracks. The machine found something the equations have no room for, something invisible that reached into those collisions, into that trillion-degree moment where the early universe briefly blinked back into existence and left fingerprints the rulebook says cannot be there. Understanding what that rulebook is, and why it was trusted so completely, is the only way to feel how significant it is that the rulebook might be wrong. 300 feet underground, the machine is still running. The beams are still circling. The collisions are still happening, 40 million per second. each one a tiny recreation of the universe's first breath. And in the debris of those collisions, something is waiting to be understood. Imagine you are handed a rule book for a game you have never played. The book is thick. Every rule connects to every other rule. You read it from the first page to the last, and it makes complete, perfect sense. You play the game 1,000 times, and the rulebook predicts every outcome correctly. You hand it to someone else. They play 1,000 more times. Same result. Scientists across every country on Earth run the same tests. Same result every time, without a single exception. You begin to believe the rulebook is complete. That is exactly where physics stood for most of the 20th century. The rulebook is called the Standard Model. Scientists built it piece by piece over roughly 50 years, starting in the 1960s and reaching its most complete form by the 1990s. It describes 12 fundamental particles of matter and 4 forces that control how those particles interact with each other. Gravity at the scale of everyday life, electromagnetism, which controls light, electricity, and the behaviour of atoms. The strong nuclear force, which holds the nucleus of every atom in the universe together. The weak nuclear force, which governs radioactive decay and powers the nuclear reactions burning inside the sun. All of it, every particle, every force, every interaction fits inside one framework. And for 50 years, every experiment ever run confirmed it. Every prediction it made turned out to be correct. The Higgs boson is the most famous example of just how accurate the Standard Model is. In 1964, a physicist named Peter Higgs and several colleagues proposed that an invisible field fills all of space. Every particle that has mass gets that mass by moving through this field. The more strongly a particle interacts with it, the heavier it becomes. The field itself should produce a detectable ripple, a particle that physicists called the Higgs boson. The model predicted this particle nearly 50 years before anyone had the technology to find it. Scientists spent decades and billions of dollars building the Large Hadron Collider specifically to search for it. On July the 4th, 2012, they found it exactly where the mathematics said it would be, with exactly the properties the equations predicted. Peter Higgs, then 82 years old, sat in the front row of the announcement auditorium at CERN and wiped tears from his eyes. That kind of accuracy builds deep trust. It makes a theory feel not just reliable, but complete, like a map that has been checked from every direction and never once been wrong. But even its creators knew the Standard Model was incomplete. They knew it from the beginning. The model has no explanation for gravity at the particle scale. Gravity is the most obvious force in the universe, the one you feel every second of your life, and yet the framework that describes every other force simply leaves it out. It works anyway, because gravity is so extraordinarily weak at the scale of individual particles that it barely affects the calculations. But leaving gravity out means leaving out a real piece of reality. The model also has no explanation for dark matter. Scientists know dark matter exists because they can measure its gravitational effect on galaxies. Galaxies spin in ways that only make sense if there is far more mass present than we can see something invisible, spread through vast halos surrounding every galaxy, holding them together with gravity while remaining completely undetectable by any telescope ever built. The Standard Model has no particle that fits that description, not even a placeholder, and the model cannot explain why the universe contains matter at all. When the Big Bang created energy that converted into particles, it should have created equal amounts of matter and antimatter. Equal amounts meeting each other should have annihilated each other completely, leaving nothing behind but light. The universe should be empty. The fact that you exist, that stars exist, that planets exist, that anything made of matter exists, has no complete explanation inside the current model. These gaps were known. Scientists assumed they would eventually extend the model to fill them, the way a growing map eventually fills in its blank edges. Then, something different arrived. Not gaps, direct contradictions. A gap says the map is missing territory. A contradiction says the map has drawn the territory wrong. Gaps are manageable. Contradictions are dangerous. And the contradictions that started arriving from CERN were not vague suggestions or borderline measurements. They were specific predictions of the standard model being tested with extraordinary precision and coming back with the wrong answer. Not slightly wrong, consistently, stubbornly, repeatedly wrong across different experiments, different teams, different particles. One senior physicist described the feeling as looking at a photograph of your house and realizing the shadow in the corner does not match anything standing in the yard. The house is still standing, everything looks fine, but something is casting that shadow, and the harder you look for what it is, the more shadows you find. There is a threshold in physics for when a result stops being noise and starts being real. Scientists call it 5 sigma. It means the result is so far from what random chance would produce that the probability of it being a fluke is less than 1 in 3.5 million. 5 sigma is the standard for claiming a discovery. Several of the anomalies now emerging from CERN have come close. Some have crossed it. And here is what makes the current situation different from every previous time a strange result appeared and then faded away under better measurement. The anomalies are not fading. They are growing. Each new dataset, each upgraded detector, each additional year of collisions adds more data pointing in the same direction. The rulebook predicted a certain world. The machine is finding a slightly different one. And the difference, small as it looks in the numbers, is enormous in what it means. Because the standard model is not just a scientific theory. It is the foundation beneath every other piece of physics built in the last 50 years. Quantum mechanics, electromagnetism, nuclear physics, cosmology, all of it rests on the standard model's framework. If part of that framework is wrong, the error does not stay contained. It spreads. It reaches into everything built on top of it. The cracks are not in a minor corner of the theory. They are appearing in the load-bearing walls. And the particles revealing those cracks, the beauty quark, the muon, the W boson, are not exotic or obscure. They are particles scientists have studied for decades, measured thousands of times, believed they understood completely. Something changed when the measurements became precise enough to see what was always there. Something hiding just beneath the surface of the most tested theory in human history. The rulebook is not broken yet, but it is bending. And in the language of physics, bending this far, this consistently, in this many places at once, means something real is pushing on it from the other side. Something the rulebook has no name for. There is a particle with a name that sounds almost romantic. The beauty quark, also called the bottom quark, depending on which physicist you ask and how poetic they are feeling that day. It is the 5th of 6 types of quarks that exist in nature and in the world of particle physics, where most exotic particles survive for fractions of a trillionth of a second before vanishing. The beauty quark is unusual. It lives slightly longer than most, long enough for detectors to watch it, travel a tiny, measurable distance before it falls apart. That tiny distance is everything. It is what makes the beauty quark one of the most valuable objects in experimental physics. To understand why, you need to understand what quarks actually are. Your hand looks solid. It feels solid. Every instinct you have tells you it is a dense, continuous object made of real, substantial stuff. Every instinct is wrong. Atoms are almost entirely empty space. If you took a single atom and expanded it to the size of a football stadium, the nucleus at the centre would be the size of a marble sitting on the 50-yard line. The electrons orbiting around it would be too small to see. Everything else, the entire rest of the stadium, would be nothing. And atoms themselves are made of smaller things. Protons and neutrons sit in the nucleus. For most of scientific history, those were considered fundamental, the smallest things that could exist. Then experiments in the 1960s revealed that protons and neutrons are themselves made of even smaller particles. Quarks. A proton contains 3 quarks, bound together by a force called the strong nuclear force, carried by particles called gluons. The quarks inside a proton are never still. They exchange gluons constantly, moving at incredible speeds, and the energy of all that motion contributes more to the proton's mass than the quarks themselves do. The solid world around you is mostly the frozen energy of particles that have never, in the entire history of the universe, stopped moving. 6 types of quarks exist: up, down, charm, strange, top and bottom. The up and down quarks make up the protons and neutrons inside every atom you have ever touched. The others are heavier, unstable, and appear only when particles collide at high energy. The beauty quark is one of these heavier types. It cannot exist in isolation, no quark can. Pull a quark away from its partners, and the energy required to separate them is so large that it spontaneously creates a new quark pair, rather than allowing the single quark to escape. Quarks are permanently imprisoned inside the particles they form, a property physicists call confinement. When the Large Hadron Collider smashes protons together, the collision produces beauty quarks in large numbers. Each one quickly combines with another quark to form a composite particle, a beauty hadron, which then travels a short distance before the beauty quark inside it decays, converting into a lighter quark and releasing a spray of other particles in the process. Those other particles are what the LHCb detector catches and measures. The standard model has precise predictions for exactly what those particles should be. Specifically, it predicts how often the beauty quark should decay into an electron versus a muon. Electrons and muons both belong to a family called leptons. They carry the same electric charge. They interact through the same forces. The only measurable difference between them is mass. A muon is approximately 200 times heavier than an electron. The standard model treats this mass difference as irrelevant for the specific type of decay LHCb was measuring. The decay rate into electrons and the decay rate into muons should be identical, equal, perfectly balanced. They were not. Across hundreds of millions of recorded beauty quark decays, LHCb found that the decay into electrons happened more often than the decay into muons. The difference was small in absolute terms, but in the precise statistical language of particle physics, it was large enough to demand a serious explanation. The property being tested has a formal name: lepton universality. It is the principle that all leptons, electrons, muons, and their heavier cousin, the tau particle, experience the fundamental forces in exactly the same way. Lepton universality is not a suggestion in the standard model. It is not a simplifying assumption. It is a structural requirement. The entire mathematical framework depends on it. If lepton universality is violated, the foundation of the model develops a crack that cannot be patched over with small adjustments. The LHCb team did not rush to publish. They checked their equipment. They checked their analysis methods. They ran the numbers through independent approaches, asking different members of the collaboration to repeat the analysis using different techniques. Collaborations like LHCb include over 1,000 scientists from institutions across the world. Results that survive that level of internal scrutiny are not easily dismissed. The result survived. It was published as a 3.1 sigma deviation, meaning the probability of it being a random statistical fluctuation was approximately 1 in 1,000. Strong enough to take seriously. Not yet strong enough under physics conventions to claim a confirmed discovery, but strong enough that theorists across the world immediately began building explanations for what could cause it. 2 candidates emerged as the leading possibilities. The first is something called a Z-prime boson. It would be a new force-carrying particle, similar in structure to the known Z boson that mediates part of the weak nuclear force, but with different properties specifically, the ability to couple more strongly to one generation of leptons than another. If a Z-prime boson exists, it would insert itself invisibly into beauty quark decays, acting like a hidden thumb on the scale, nudging the decay rate toward electrons and away from muons. Its effects would be too subtle to see in any single event, showing up only as a statistical pattern across millions of decays, exactly the pattern LHCb was measuring. The second candidate is even more dramatic. A leptoquark. In the standard model, quarks and leptons are completely separate families. They do not interact directly. A leptoquark would be a particle that bridges that gap, creating a new pathway for quarks to decay into specific leptons more than others. Its existence would not just add a new particle to the model, it would introduce an entirely new category of interaction and connection between 2 families of particles that the current framework insists are unrelated. Neither a Z-prime boson nor a leptoquark has been directly detected. But here is what makes the beauty quark result more than an interesting footnote. It did not stand alone. As the LHCb collaboration continued collecting data and refining its analysis, the pattern of anomalies in beauty quark decays grew broader. Multiple decay channels, not just one, showed deviations from prediction. The overall picture of beauty quark behavior remained inconsistent with the standard model across several independent measurements simultaneously. A single anomalous number can be explained away. A consistent pattern across multiple measurements, multiple decay pathways, multiple years of data that is something else entirely. That is a signal. And in physics, a signal has a source. Something is influencing beauty quark decays in a way the standard model has no mechanism to produce. Something invisible, reaching into those collisions from outside the boundaries of the current framework, and leaving its mark in the one place sensitive enough to detect at the precise ratio of how often a particle chooses one path of decay over another. The beauty quark confessed. In the quiet, statistical language of a million measurements, it told scientists that something is present that the rulebook says cannot be there. And at almost exactly the same time, from a completely different machine, measuring a completely different particle, another confession was being recorded. This one involved a particle raining through your body right now. A particle so familiar to physicists, so thoroughly studied, that finding it misbehaving felt like discovering that gravity pulls slightly sideways on Tuesdays. The muon was spinning wrong, and the implications of that single fact would reach further than almost anyone expected. Right now, as you listen to this, roughly 10,000 muons are passing through your body every minute. You cannot feel them. You will never feel them. They arrive from above, born high in the atmosphere, when cosmic rays, high-energy particles, travelling in from deep space slam into the air roughly 30 miles above your head. That collision produces a cascade of secondary particles, and many of them are muons. They travel downward at speeds close to the speed of light, passing through the atmosphere, through buildings, through your body, and into the ground beneath your feet, all without leaving a single trace. They are like ghost bullets, passing through matter with almost no resistance at all. A muon is, in almost every way, a heavy version of the electron. It carries the same negative electric charge. It responds to the same forces. The only real differences are that it weighs about 200 times more than an electron, and it does not last. A muon survives for only about 2/millionths of a second before it decays into an electron and 2 neutrinos. 2/millionths of a second sounds impossibly brief, but for an unstable particle, it is remarkably long. Most exotic particles produced in high-energy collisions survive for fractions of a trillionth of a second. A muon lives long enough to fall from the upper atmosphere all the way to the surface of the Earth. That is only possible because of a genuine, measured effect from Einstein's theory of relativity called time dilation. Fast-moving objects experience time more slowly relative to a stationary observer. The muon ages more slowly during its high-speed fall, which is the only reason it survives the journey at all. This is not a theoretical curiosity. It is measured physics, confirmed every single day by particles falling through the sky above you. Here is the property that made the muon useful to physicists chasing anomalies. A muon behaves like an extremely small magnet. It has what is called a magnetic moment, meaning it responds to magnetic fields by spinning, the way a compass needle responds to the Earth's magnetic field. The standard model predicts exactly how strong that magnetic moment should be. Physicists represent this number with the letter G, and the model says G should be almost exactly 2, with an extremely small correction caused by quantum effects. That tiny correction is called G minus 2. And the calculation of what its exact value should be, according to the standard model, is one of the most precisely computed numbers in the history of physics. Decades of theoretical work, summing contributions from enormous numbers of quantum interactions, went into predicting it. Scientists built an entire experiment at Brookhaven National Laboratory in New York specifically to measure the real value and compare it to the prediction. In 2001, the results came in. The measured value did not match the theoretical prediction. The gap was small, but it was consistently present, in the same direction every time they ran the experiment. The interpretation scientists proposed was simple to state and enormous in its implications. Something beyond the standard model was interacting with the muon during its brief life, adding a tiny extra push to its magnetic moment. Something invisible to the current framework, but real enough to leave a measurable mark. They called it a new physics signal. For nearly 20 years, that result sat in the scientific literature as an intriguing but unconfirmed anomaly, strong enough that physicists could not dismiss it, isolated enough that many assumed a better, more precise measurement would eventually explain it away as an error. Then came Fermilab. To confirm the Brookhaven result, scientists needed the same magnet the actual physical ring used in the original experiment moved from New York to a new facility in Illinois. This was not a simple shipping job. The magnet is 50 feet wide and weighs 17 tons. It could not be tilted more than a fraction of a degree, because the superconducting coils built into it over decades would shift out of alignment if disturbed. It could not be flown on any aircraft. It could not be disassembled and rebuilt, because any new world would introduce imperfections that would ruin its precision. So they drove it, slowly, on a custom-built transport vehicle, along a carefully planned route that avoided highway overpasses and sharp turns. The journey from New York to Illinois took 35 days. Crowds came out at night to watch the enormous ring roll through their towns at 3 miles per hour. It arrived without incident. Scientists spent years setting it up inside a new facility at Fermilab, calibrating every component with extraordinary care. The experiment works by producing muons inside a small accelerator, injecting them into the large magnetic ring, and letting them circulate. As the muons travel around the ring, their spin wobbles a motion called precession, and the rate of that wobble reveals the muon's true magnetic moment. The magnetic field inside the ring is controlled so precisely that a temperature change of less than 1,000th of a degree Fahrenheit would affect the result. Every possible source of interference was tracked and accounted for. The result, the muon's magnetic moment, was higher than the standard model predicted, the same direction as Brookhaven's original finding. A stronger deviation, built from more data, collected across multiple experimental runs. When scientists combined the Fermilab results with the original Brookhaven measurement, the combined significance reached 4.2 sigma, close enough to the 5 sigma threshold used to declare an official discovery that the entire physics community began paying very close attention. Something is adding energy to the muon's magnetic moment. Something the standard model did not put there. The debate that followed was not just about whether the anomaly was real, but about what it might mean. One possibility is that the theoretical calculation itself contains a small error calculating G-2 requires summing an enormous number of quantum contributions. And if any of the underlying assumptions are slightly off, the predicted value shifts. In 2021, a group of theorists calculated one particular contribution using a new technique, and their results shifted the prediction closer to what was actually measured, reducing the size of the apparent gap. This calculation remains under active debate. Some methods support a smaller discrepancy. Others support the original, larger one. But even under the most favourable interpretations, a meaningful gap between prediction and measurement still remains. And it is not an isolated gap. It sits alongside the beauty quark anomaly, the two of them pointing, independently, toward the same missing piece. Two completely different experiments. Two completely different particles. Two different machines on two different continents. Both finding evidence of something the current framework cannot explain, and then, arriving from a third and completely unexpected direction, a measurement landed that pushed the entire conversation past speculation and into something the physics community began calling, without exaggeration, a crisis. It involved a particle whose mass was supposed to be one of the most exactly calculable numbers in all of physics. It came out wrong, and the size of the error was almost impossible to explain away. Some numbers in physics are not meant to move. The mass of the W boson is one of them. It is a particle that carries the weak nuclear force, the force responsible for radioactive decay, and the same force that powers the nuclear reactions burning inside the sun. Its mass is not an isolated fact sitting off to the side of the theory. It is woven directly into the architecture of the standard model, connected through precise, mathematical relationships to the strength of the electromagnetic force, the strength of the weak force, and the masses of other particles. Change the W boson's mass, even slightly, and you are not adjusting one number. You are pulling on a thread that runs through the entire framework. That is why, in April of 2022, a small change in that number sent a shockwave through the physics community. A team of scientists working with the Collider detector at Fermilab, a facility in Illinois, published a measurement they had spent nearly a decade refining. It was the most precise measurement of the W boson's mass ever made. Scientists described the achievement as a tour de force of experimental physics, 40 years of collected data, processed through nearly 10 years of careful analysis using the most advanced statistical techniques available. The result came out heavier than the standard model predicted, not by a small, forgivable margin, by a gap large enough that, if the measurement holds up, the standard model's prediction for the W boson's mass is simply incorrect. Here is the size of the discrepancy in real numbers. The Fermilab team measured the W boson's mass at approximately 80,433 megaelectron volts. The standard model predicted roughly 80,357 megaelectron volts. In everyday terms, that gap looks almost invisible, a tiny sliver of a percentage. But in the language of measurement precision that particle physicists use, it is enormous. The team reported the result at 7 sigma, nearly double the 5 sigma threshold that marks an official discovery. A 7 sigma deviation has less than a 1 in a trillion chance of being a random statistical fluke. To understand why measuring the W boson's mass at all is so difficult, you have to understand that the particle does not sit still long enough to be weighed directly. It appears during a collision and decays in roughly 1/10 of a trillionth of a second. Everything scientists know about its mass comes from studying the debris it leaves behind specifically, the particles it decays into. When a W boson decays, it produces a lepton, which detectors can measure directly, and a neutrino, which passes straight through the detector without leaving any signal at all. Scientists have to infer the neutrino's properties indirectly, using the principle of conservation of energy, essentially working backward from what is missing to figure out what must have been there. That kind of indirect measurement introduces uncertainty, and reducing that uncertainty to the level needed for a truly precise result requires enormous amounts of data. The final analysis used over 4 million recorded W boson decays. The team also had to calibrate every part of their detector with extraordinary precision, magnetic field strength, material thickness, detector geometry, all tuned using other well-understood particles as reference points, essentially teaching the instrument using known answers before trusting it with an unknown one. The number that came out of all that painstaking work was heavier than the model allowed. The physics community's first reaction was not celebration, it was caution. A single experimental result, even one measured at 7 sigma, requires independent confirmation before it can be trusted to overturn 50 years of validated theory. And there was reason for caution here specifically, because earlier measurements of the W boson's mass already existed, made by a different collider, the Large Hadron Collider, which had operated at CERN in previous decades. Those earlier measurements were consistent with the standard model's prediction. The new Fermilab result did not just disagree with the theory. It disagreed with previous experimental measurements too. Scientists began asking the obvious question: could the Fermilab analysis contain a hidden systematic error, a wrong assumption buried somewhere in the analysis pipeline, a miscalibrated piece of equipment, a subtle bias in how events were selected for the final dataset. The team had spent years checking for exactly these possibilities, using a method called blind analysis, where researchers finalize every methodological choice before they are allowed to see the actual result, a safeguard designed specifically to prevent unconscious bias from shaping the outcome. They found nothing wrong. Other independent groups reanalyzed the same raw data using different statistical methods. Some confirmed the higher value, others found smaller deviations. The debate has not been resolved. Then, in 2023, scientists reanalyzed the older Large Electron Positron Collider data using modern techniques that had not been available when the original measurements were made. That reanalysis also produced a W boson mass slightly higher than the standard model's prediction, though the deviation was smaller than what Fermilab had found. Around the same time, a separate independent CERN measurement came out closer to the original prediction. So now there are 3 sets of results. 2 pointing higher than the model allows, 1 landing closer to where the theory says it should be. None of them fully agreeing with each other. That level of disagreement between multiple high-precision experiments is itself remarkable. Either several separate measurements, built using entirely different equipment and entirely different methods, happen to share the same kind of hidden error, which is considered nearly unthinkable given how differently each experiment was designed, or the W boson's mass genuinely is not sitting where the standard model says it should be. And if that second possibility is true, the consequences ripple outward through the entire theory. Because the W boson's mass is not calculated alone. It is derived mathematically from other fundamental values: the strength of the electromagnetic force, the strength of the weak force, and the masses of related particles. Those relationships are treated as fixed mathematical identities inside the theory. If the W boson's actual mass is truly heavier than predicted, then one of those other values that physicists have measured independently, and which have always matched each other and the model beautifully, must also be slightly wrong. A flaw in that part of the framework is not a small patch. It is a flaw in what physicists call electroweak theory, the very structure that explains how atoms hold together, how radioactive decay works, and how the sun generates the energy that reaches Earth every single day. It would not be a minor correction tucked into a footnote. It would be a crack in a load-bearing wall. What makes the W boson anomaly especially hard to dismiss is where it came from. It did not emerge from an untested machine or an inexperienced team. It came from one of the most carefully calibrated detectors in the history of Fermilab, built and refined over 4 decades, analysed by scientists using every safeguard available to prevent bias or error, and it arrived at almost the exact moment the beauty quark anomaly and the muon anomaly were already being taken seriously by the wider physics community. 3 separate results, 3 separate particles, 3 separate machines, all pointing independently toward the same unsettling possibility that the framework holding together 50 years of physics has a gap in it, a gap that keeps appearing in different corners of the theory, as though something on the other side is quietly pressing against the walls, testing where they might give way. What that something might be, and why its existence connects directly to the biggest unanswered question about why the universe contains anything at all, takes us back to the very first moment after the Big Bang, when matter and its opposite were locked in a struggle that should have ended in absolute nothingness. 1 second after the Big Bang, the universe was a fireball beyond imagination. Inside that fireball, pure energy was converting into matter at an incredible rate. Particles were appearing out of raw heat and light, blinking into existence everywhere at once. And here is the detail that should stop you cold for every single particle of matter that appeared. An identical particle of antimatter appeared right alongside it. Antimatter is not science fiction. It is real. Scientists create it in laboratories today, including at CERN. It behaves almost exactly like ordinary matter in every measurable way, except for one crucial difference. When a particle of matter meets its antimatter counterpart, the two annihilate each other completely. Both vanish in a flash of pure energy. No residue, no survivors, just light. According to the math, every proton created in that first fireball should have had an antiproton to cancel it out. Every electron should have had an anti-electron. Every quark, an antiquark. Equal amounts of each, meeting and destroying each other in perfect balance. The universe should have been left with absolutely nothing but light and empty space. You exist. Which means somewhere in that first second, the math didn't play out the way it was supposed to. Something went wrong, or rather something went right, in a way we still don't fully understand. The victory of matter over antimatter was not dramatic. It was almost invisible. For every billion antimatter particles created, there were 1 billion and 1 matter particles. A surplus of exactly 1 out of a billion. That is the entire margin by which the universe exists at all. That tiny leftover is everything you have ever seen or touched. Every star burning in the sky, every planet orbiting those stars, every galaxy stretching across billions of light years. Every human being who has ever lived all of it is built from that single leftover particle in a billion. Scientists call this imbalance matter-antimatter asymmetry, and it is one of the oldest and deepest unsolved problems in physics. The Standard Model does not ignore this problem completely. It acknowledges that some asymmetry should exist, and it even predicts a small amount of it through a mechanism called charge parity violation, usually shortened to CP violation. Here is what that phrase actually means in plain terms. When certain particles decay, they don't always treat matter and antimatter identically. One version of a decay process might happen slightly more often than its mirror image antimatter version. That small, consistent preference is CP violation, and it is one of the conditions physicists believe could have allowed matter to pull ahead of antimatter in the early universe. Scientists first confirmed CP violation in 1964, studying a particle called the neutral kaon. It was a genuine breakthrough, and it earned a Nobel Prize. But when researchers calculated exactly how much asymmetry the kaons produced, the number came out far too small, billions of times too small to explain the matter surplus that actually exists in our universe. So physicists went looking elsewhere. They turned their attention to particles containing beauty quarks, the same particles at the centre of the lepton universality anomaly, because the Standard Model predicted they should show a much stronger form of CP violation than kaons ever could. CERN built the LHCb experiment partly to test this directly, and they did find CP violation in beauty quarks. More than in kaons, certainly, but still not enough. Still nowhere near the level required to explain why the universe contains stars and planets and people instead of empty space. Every time scientists measure CP violation in a new particle and come up short of what's needed, the same unanswered question grows louder. Where is the rest of the imbalance coming from? What produced the extra push needed to leave the universe with a surplus of matter, 1 part in a billion? One possibility, taken seriously by a growing number of physicists, is that the missing asymmetry came from a source the standard model simply cannot see: a new particle, or a new force, active only in the extreme conditions of the very early universe, that produced far more CP violation than anything measurable today. That hidden source would have done its work billions of years ago and then effectively disappeared, leaving behind only one piece of evidence: a universe full of matter. Which is exactly what we observe. Scientists at CERN have been hunting for traces of that hidden source, not by looking for it directly, since it may no longer exist in any detectable form, but by looking for its lingering effects on particles today. If something beyond the standard model shaped the earliest moments of the universe, it likely still leaves tiny, hard-to-measure fingerprints on particle behavior right now. That is the entire logic behind the beauty quark experiments at LHCb. Measure enough decays with enough precision, and any hidden influence should eventually show up as a small but persistent statistical deviation. It showed up. In 2019, the LHCb collaboration announced they had observed CP violation for the first time in a particle called the D meson, which contains a charm quark. The standard model had predicted that CP violation would exist in this particle, but that it would be extremely small, far too small, to measure with the technology available at the time. LHCb measured it anyway, and the value came out larger than the prediction allowed. A larger than expected CP violation in a particle where the theory expected almost nothing means one of two things. Either the underlying calculation has an error, or an additional, unaccounted for source of CP violation, exists something operating outside the boundaries the standard model has drawn. Theorists immediately began constructing models in which a new undiscovered particle could explain the surplus CP violation in this system. And strikingly, several of those same theoretical models also predict effects that would show up in the beauty quark decays already flagged as anomalies elsewhere. The threads keep tying back to the same place. CERN is now running the Large Hadron Collider at higher intensity than ever before, colliding particles more frequently and gathering larger datasets of both beauty and charm quark decays than at any point in its history. Every additional decay recorded is another data point. Every data point either weakens the case for new physics or strengthens it. Right now, the case is strengthening. There is something quietly emotional about this particular mystery, more than almost any other anomaly in physics. The question of why matter outnumbered antimatter is not an abstract curiosity confined to laboratories and equations. It is the answer to why anything exists at all. Why the universe became a place filled with galaxies and oceans and living things, rather than an endless, silent expanse of light with nothing left to observe it. Antimatter research continues at CERN through dedicated experiments that trap antihydrogen atoms, the antimatter version of the simplest element in existence, and measure their properties with extraordinary precision, searching for any tiny difference between matter and antimatter that the standard model might have missed. So far, antihydrogen looks almost identical to ordinary hydrogen. Almost, small statistical hints keep appearing at the very edge of what current instruments can measure. Hints too faint to confirm, too persistent to dismiss. Somewhere in that faint, flickering signal may be the answer to why you are here to hear this story at all. And the search for that answer leads directly into a question that stretches beyond particle physics, entirely into the possibility that the four forces holding the universe together are not the only forces that exist. Four forces run the entire universe. Gravity holds planets in their orbits and keeps your feet on the ground. Electromagnetism controls light, electricity, magnetism, and the way atoms bond together to form everything solid around you. The strong nuclear force holds the nucleus of every atom together, fighting against the natural repulsion between positively charged protons packed tightly inside it. The weak nuclear force governs radioactive decay and powers the nuclear reactions burning inside the sun right now, producing the light and warmth that reaches Earth 8 minutes later. Four forces. For over half a century, every physical event ever observed, every collision, every decay, every interaction between particles anywhere in the universe has fit inside those four categories. No exceptions. No fifth option needed. But the anomalies now emerging from CERN keep pointing towards something the four known forces cannot explain. Something that behaves like a force, but doesn't match the description of any of the four already on the list. The idea of a fifth force is not brand new. Physicists have proposed versions of it for decades, usually in response to some strange, unexplained result. And historically, most of those proposals quietly faded away once better measurements came along and explained the anomaly using ordinary physics instead. Inside the field, the fifth force became something of a running joke, a placeholder people reached for when they didn't have a better answer yet, more hope than evidence. The current situation feels different, and here is why. The anomalies driving this new fifth force conversation are not coming from one team, one machine, or one strange result that nobody else has managed to reproduce. They are coming from a cluster of independent measurements, the beauty quark decays at LHCb, the muon's magnetic moment at Fermilab, the mass of the W boson, the unexpectedly large CP violation in charm particles. Different machines, different particles, different research teams working independently of each other, sometimes without even knowing about each other's results in advance. And yet they are all showing deviations that point, again and again, toward the same missing piece in the standard model. A fifth force, if it exists, would be a new type of interaction carried by a new type of particle, operating under rules the current framework simply does not contain. Depending on its exact properties, it might only affect certain kinds of particles and leave others completely untouched. It might operate only over extremely short distances, smaller than the width of an atomic nucleus, which would explain why it has never shown up in any large-scale experiment before now. It might be extraordinarily weak at the energy levels we experience in everyday life, only becoming detectable in the extreme precision of modern particle physics experiments, the kind capable of measuring the tiniest deviations across hundreds of millions of events. Several concrete theoretical candidates have already been proposed to explain what this force might actually be. The first is the Z prime boson, which we touched on earlier in connection with the beauty quark anomaly. It would be a new force-carrying particle, structurally similar to the already known Z boson that helps mediate the weak nuclear force, but with a key difference: it would couple more strongly to certain types of leptons than to others. If a Z prime boson exists, it would quietly influence beauty quark decays, subtly favouring the production of electrons over muons in a way that matches exactly what LHCb has been measuring. The second candidate emerged specifically in response to the muon's misbehaving magnetic moment. Physicists call it a muon-philic boson, a particle that interacts specifically and strongly with muons, far more than it interacts with electrons. If such a particle exists, it would constantly nudge the muon during its brief lifetime, adding a small extra contribution to its magnetic moment that no calculation, using only the known four forces, could ever produce. This candidate fits the muon anomaly with unusual precision. Neither particle has ever been directly detected. Both remain theoretical, built from equations and predictions rather than confirmed observation. But the signals they were designed to explain refuse to disappear, no matter how many times scientists check their instruments, refine their calculations, or collect more data. And in 2023, a completely separate result added yet another data point to the growing picture. A laboratory in South Korea, measuring the behavior of electrons at very low energies, found a small deviation consistent with what a new, extremely light boson would produce if it existed. The result was not independently confirmed, and its statistical significance fell below the threshold required to call it a discovery, but it landed in the same direction as everything else, another small, quiet piece of evidence pointing toward the same gap in the wall. If a fifth force is real, it would not simply be added to the end of the current list, like an afterthought tacked on to an otherwise finished theory. It would mean that the framework physicists have relied on for 50 years tested, retested, confirmed across every experiment ever run, is actually a smaller piece of something much larger. A map that got most of the visible territory right, but missed an entire hidden region just beyond its edges. Here is what makes this particular moment in physics feel different from the false alarms of the past. Every few years, a new data set arrives, either strengthening the case for a fifth force or weakening it. Right now, across multiple independent lines of evidence, the case is stronger than it has been at any point in living memory. Not proven, not confirmed, but stronger and growing stronger with every new run of the machine. Consider what a discovery like this would actually mean if it were confirmed. The last time physics encountered something structurally similar was the discovery of the weak nuclear force itself, in the middle of the 20th century. Before that discovery, scientists only knew about gravity and electromagnetism, two forces that had been understood, in some form, since the era of Newton and Faraday. The weak force was something entirely new, a completely different category of interaction that required new particles, new mathematics, and a genuine expansion of the entire theoretical framework that existed at the time. Finding a fifth force now would be even bigger. The standard model, as it currently exists, is a far more complete and sophisticated structure than anything physicists had before the weak force was understood. Adding a genuinely new force to that structure would not be a minor correction. It would be a fundamental expansion of the map of reality itself, one with consequences reaching far beyond particle physics and deep into the biggest unanswered questions in all of science. A confirmed fifth force could help explain why beauty quarks decay the way they do. It could explain the muon's stubbornly incorrect magnetic moment. It might even connect, in ways current theorists are only beginning to explore, to the two biggest mysteries hiding in plain sight across the entire universe: the invisible mass holding galaxies together, and the invisible pressure pushing the universe apart faster and faster with each passing moment. Those two mysteries have a name. Dark matter and dark energy make up roughly 95% of everything that exists, and the standard model, for all its extraordinary precision, has absolutely nothing to say about either of them. Understanding how the fifth force hypothesis might connect to that vast, invisible majority of the universe requires stepping back from particle collisions altogether, and looking instead at the galaxies spinning silently overhead, moving in ways that gravity alone cannot explain. Everything you have ever seen is a minority. Every star in the night sky, every planet, every cloud of gas drifting between galaxies, every human being who has ever lived all of that visible matter adds up to only about 5% of everything that exists in the universe. The rest is invisible, and for most of scientific history, nobody even knew it was there. Scientists first suspected something was missing in the 1930s, when a Swiss astronomer named Fritz Zwicky noticed that galaxies inside large galaxy clusters were moving far too fast. Using the laws of gravity as they were understood, the visible matter in those clusters simply did not have enough mass to hold everything together at those speeds. The galaxies should have been flying apart. They weren't. Something with real mass, something producing real gravity, had to be present that no telescope could detect. Decades later, further measurements confirmed and deepened the mystery. Scientists studied how individual galaxies rotate and found something strange. Stars near the outer edges of a galaxy were orbiting just as fast as stars closer to the centre. Under normal gravity, that should not happen the way planets farther from the Sun take longer to complete their orbits. Stars farther from a galaxy's centre should move more slowly too. They don't. Something massive, spread out in a vast invisible halo surrounding the entire galaxy, was providing extra gravitational pull that reached all the way to the outer edges. Scientists named that invisible substance dark matter, and to this day, nobody knows what it actually is. Dark matter does not emit light, it does not reflect light, it does not absorb light. No telescope ever built, no matter how powerful, can see it directly. The only reason scientists know it exists at all is because of its gravity. Its effect on the motion of galaxies is unmistakable, even though the source of that effect remains completely hidden. Dark matter makes up roughly 27% of everything in the universe. Compare that to the 5% made of ordinary, visible matter, and you start to see just how small a slice of reality we can actually observe. The Standard Model has no particle that fits the description of dark matter. Not one. Dark matter clearly interacts through gravity, but it does not interact through electromagnetism, which is exactly why it stays invisible. Every particle currently described by the Standard Model interacts through at least one of the other three forces in some measurable way. Dark matter fits none of the existing categories. There is no slot for it, no placeholder waiting to be filled in. One leading theoretical candidate is a particle physicists call a WIMP short for weakly interacting massive particle. The name describes exactly what it would be. A particle with real mass, interacting through the weak nuclear force, but not through electromagnetism at all. A particle like this would be invisible, capable of passing through ordinary matter with only extremely rare interactions. And it would cluster together under gravity in exactly the kind of vast, galaxy-spanning halos that astronomers have already observed. It would also naturally produce roughly the correct amount of dark matter to match what we see in the universe today. Here is where CERN enters this particular mystery directly. If weakly interacting massive particles exist, they should be produced occasionally inside high-energy collisions, exactly the kind of collisions happening 40 million times a second inside the Large Hadron Collider. Scientists have searched repeatedly through years of collision data, looking for the specific signature such a particle would leave behind. So far, no confirmed detection has emerged, but the anomalies already discussed change the picture in an interesting way. If a new particle exists that is responsible for the beauty quark deviations or the muon's incorrect magnetic moment, it must have properties that place it outside the Standard Model entirely. And some of those required properties overlap surprisingly well with what a dark matter particle would need to have. A force carrier that couples differently to different types of leptons, for example, is already a new kind of particle by definition. That same particle might also interact with dark matter, linking two of physics' biggest open mysteries together through a single, still undiscovered connection. No confirmed link exists yet. This remains a theoretical possibility rather than an established fact. But multiple independent research teams have already built working models in which a single new particle could explain both the flavor anomalies showing up at CERN and the correct density of dark matter observed across the universe simultaneously. If a particle like that is ever found, it would not solve one mystery. It would solve two of the biggest open questions in modern physics at the exact same time. The search for dark matter runs constantly alongside every other analysis happening at CERN. Detectors are built to watch for a very specific kind of event or particle that appears briefly during a collision and then vanishes without leaving any further trace, carrying energy away in a way that never shows up anywhere in the detector. Since dark matter would not interact electromagnetically, this is exactly the kind of invisible exit it would make. Scientists call this signature missing energy, and it happens constantly inside the Large Hadron Collider. Most instances have completely ordinary explanations, but a small fraction remain unexplained even after every known possibility has been carefully ruled out. That small, stubborn fraction is where a great deal of careful, patient research time is currently being spent. Dark matter is only half of the invisible universe. The other half is even stranger. In the late 1990s, two independent teams of scientists were studying distant supernovae, massive exploding stars, bright enough to be seen from billions of light years away, using them as reliable markers to measure how quickly the universe has expanded over time. The expectation going in was straightforward. Gravity, pulling on all the matter in the universe, should be gradually slowing that expansion down over time. The data showed the exact opposite. The universe was not slowing down, it was speeding up. Something was pushing space apart faster and faster as time went on, with enough energy to overcome the combined gravitational pull of every object in the observable universe. Scientists named this unknown force dark energy, and they know even less about it than they know about dark matter. Dark energy makes up roughly 68% of everything that exists. Add it to dark matter's 27%, and together the two unknown substances account for 95% of the entire universe's content. The standard model the framework physicists have tested and trusted for 50 years addresses exactly 0% of that 95. One especially unsettling detail connects dark energy directly back to particle physics. Quantum mechanics predicts that even completely empty space should contain a small but real amount of energy, caused by particles flickering briefly in and out of existence everywhere, all the time. When physicists calculate how much energy that empty space should carry, using the tools of particle physics, they get one number. When astronomers measure the actual energy driving the universe's expansion, they get a wildly different number, different by a factor of 10, followed by 120 zeros. Scientists sometimes call this the worst prediction in the entire history of physics, and nobody has ever fully explained the gap. 95% of the universe remains almost entirely unexplained, and the anomalies emerging from CERN, small as they are, may be the very first fingerprints of whatever fills that enormous silent gap. The next clue, strangely enough, comes not from a hidden particle at all, but from one the standard model insisted for decades had absolutely no mass whatsoever until it was caught doing something the equation said was flatly impossible. Right now, about 100 billion neutrinos from the Sun are passing through every square inch of your body every second. You will never feel them. In the time it takes you to read the sentence, roughly 1 trillion neutrinos will have travelled completely through your body at nearly the speed of light, entering through the top of your head, passing through every organ, every bone, every cell, and exiting through your feet without disturbing so much as a single atom along the way. They are ghost particles, so weakly interactive with matter that a solid wall of lead, stretching from here to the nearest star, would stop only about half of them. Neutrinos are produced whenever atomic nuclei change in the nuclear reactions burning inside stars, in radioactive decay happening naturally in rocks and soil, in cosmic ray collisions high in the atmosphere. The Sun alone produces them in such vast quantities that they outnumber every other type of particle in the universe by roughly 1 billion to 1. And for most of the Standard Model's history, physicists were absolutely certain of one fact about them. Neutrinos had no mass at all. Massless particles, according to the equations, cannot change. They are locked into their identity permanently. An electron neutrino produced in the Sun's core should arrive at Earth 8 minutes later as an electron neutrino, unchanged, exactly as it started. A muon neutrino from a cosmic ray collision should remain a muon neutrino for the entire length of its journey across space. 3 types exist: electron neutrinos, muon neutrinos, and tau neutrinos, each paired with its corresponding charged lepton, each completely stable, each maintaining its type forever. Then, in the late 1990s, experiments detected something that the Standard Model declared impossible. Neutrinos were changing from one type to another during their travel, spontaneously shifting identity mid-flight like cosmic shapeshifters. An electron neutrino produced in the Sun could arrive at Earth as a muon neutrino. A muon neutrino could transform into a tau neutrino during its journey through space. Scientists had actually been circling this discovery for decades without fully recognizing what they were seeing. In the 1960s, a physicist named Ray Davis built a detector deep underground in a gold mine in South Dakota, specifically designed to catch neutrinos coming from the Sun. The detector used a tank containing 600 tons of cleaning fluid, ordinary household cleaning fluid, chosen because it contains chlorine atoms that react in a specific detectable way when struck by a neutrino. Davis measured how often these reactions happened and compared the rate to what the Standard Model predicted based on the known nuclear processes inside the Sun. The numbers didn't match. Davis was detecting only about 1/3 the number of electron neutrinos the theory said should be arriving. The discrepancy was consistent, persistent, and completely mystifying. Either something was fundamentally wrong with scientists' understanding of how the Sun worked, which seemed unlikely, given how well other solar observations matched theoretical models, or something was happening to the neutrinos during their journey from the Sun's core to Earth. The answer came from experiments in Japan and Canada designed to study neutrinos produced much closer to home. The Super Kamiokande detector in Japan, built inside a massive underground cavern and filled with 50,000 tons of ultra-pure water, was sensitive enough to detect the tiny flashes of light produced when neutrinos occasionally collided with water molecules. The Sudbury Neutrino Observatory in Canada used a completely different detection method, employing a sphere containing 1,000 tons of heavy water suspended inside a larger chamber lined with thousands of light detectors. Both experiments confirmed that neutrinos were indeed changing type, oscillating between their different identities as they travelled. The electron neutrinos produced in the Sun were transforming into muon and tau neutrinos during their 8-minute journey to Earth, which explained perfectly why Davis had been detecting only a fraction of them. His detector was only sensitive to the electron type, missing all the others that had changed identity along the way. Here is the crucial detail that made this discovery more than just an interesting observation. Neutrino oscillation requires mass. The mathematical relationship is explicit and unavoidable. For neutrinos to change from one type to another, the 3 different types must have different masses, even if those masses are extremely tiny. Massless particles cannot oscillate between types under any circumstances. The standard model said neutrinos were massless. The neutrino oscillation experiments proved they had mass. This was not a subtle deviation or a slight discrepancy in a decimal place. It was a categorical contradiction. The model said a thing could not happen. And the thing was happening. 2 physicists who led the key experiments confirming neutrino oscillation, Takaaki Kajita and Arthur MacDonald, were awarded the Nobel Prize in Physics in 2015. The discovery was celebrated as a major breakthrough, proof that the standard model was incomplete in a fundamental way. And then the physics community did something remarkable. They moved on without actually fixing the underlying problem. The standard model was informally patched. Mass terms for neutrinos were added to the equations by hand, without any deeper explanation of where those masses come from or why they exist. The hole in the theory was covered, but the cause of the hole was never identified. The framework that had been tested and trusted for decades suddenly had a gap that everyone acknowledged, but no one fully resolved. This pattern, anomaly, discovery, patch, move on, established a troubling precedent. It demonstrated that even a direct, confirmed violation of the standard model's predictions could be accommodated through adjustments rather than genuine revision. The model's foundations remained untouched, even when those foundations had been shown to be incomplete. One proposed explanation for neutrino mass involves a theoretical particle called the sterile neutrino. Unlike the 3 known types, which interact through the weak nuclear force, a sterile neutrino would interact only through gravity. It would be completely invisible to every detector ever built, even more elusive than ordinary neutrinos. Sterile neutrinos are considered one of the leading candidates for dark matter. They would be produced in the early universe, interact gravitationally to form the halos surrounding galaxies, and remain completely undetectable through any direct measurement. Several experiments have reported tentative hints of sterile neutrinos over the years, usually in the form of small but persistent deficits in measured neutrino rates. The reactor antineutrino anomaly, detected at nuclear power plants around the world, shows fewer electron antineutrinos arriving at detectors than the theoretical production rate suggests should be created. The deficit is small, only a few %, but it is consistent across multiple reactor sites in different countries over many years. If electron antineutrinos are oscillating into sterile ones during their short journey from reactor to detector, those sterile neutrinos would become completely invisible upon arrival, explaining the shortage. None of these hints have been confirmed as discoveries. They exist in the scientific literature as unresolved anomalies, too persistent to dismiss, but too weak to definitively confirm. The pattern feels familiar: small, stubborn deviations from prediction that refuse to disappear, no matter how carefully the experiments are repeated or refined. The neutrino mass discovery was the first direct experimental proof that the standard model is incomplete. It was confirmed beyond any reasonable doubt, celebrated with a Nobel Prize, and then essentially set aside through theoretical patches rather than genuine understanding. Every subsequent anomaly emerging from CERN follows the same template, a result the model cannot explain, pointing towards something beyond the current framework's boundaries. But the neutrino discovery introduced a new element that makes the current moment feel different. The possibility that the missing pieces are not just single particles or isolated effects, but entire categories of physics operating in dimensions of space that human intuition cannot directly access. You experience 3 dimensions of space: left and right, forward and back, up and down. Move your hand in any direction you choose, and it will travel along one of these 3 lines, or some combination of them. Add time to those 3 dimensions of space, and you have the 4-dimensional framework that describes every event you have ever experienced and every measurement any instrument has ever recorded in the history of science. 4 dimensions total. It feels complete, natural, obvious, the full extent of reality itself. But the mathematics of theoretical physics does not stop at 4. String theory, one of the most promising approaches to building a complete theory of nature, requires 10 dimensions to be mathematically consistent. Some versions require 11. The extra dimensions are not optional decorations added for elegance or philosophical satisfaction. They are mathematical necessities. If the equations describing the fundamental structure of matter are correct, then those additional dimensions must exist. So why do you not experience them? Why can you not point in the direction of the 5th dimension, or the 7th, or the 10th? One explanation is size. Imagine a garden hose viewed from far away. It looks like a one-dimensional line stretching across your field of view. But move closer, and the truth becomes clear: the hose's width. A circular dimension curled around itself that was invisible from a distance. An ant walking on the surface of that hose would experience 2 dimensions, forward and backward along the length, and around the circumference. You, looking from far away, see only 1. Extra dimensions might be curled up in exactly the same way, but at a scale so small that no instrument humans have ever built could detect them. At every point in the 3-dimensional space you can move through, there might be additional tiny dimensions, twisted and folded into shapes so compact they disappear into the quantum foam that exists at the smallest possible scales of measurement. 6 additional directions you cannot point to, because they exist only across distances smaller than the width of an atomic nucleus, smaller than a proton, smaller than a quark. But there is another possibility, stranger and more unsettling. What if the extra dimensions are not small at all? What if they are large, even infinite, but you cannot access them because you are stuck to a surface? Imagine a perfectly flat table that stretches in all directions forever. Now imagine that every particle of matter that has ever existed, every atom in your body, every star in the sky, every planet and moon and grain of cosmic dust, is somehow confined to slide along the surface of that table, able to move left and right and forward and back across the tabletop, but never able to rise even a fraction of an inch above it or sink below it. From your perspective, trapped on that surface, the table would appear to be the entire universe, 3 dimensions of space, plus time. But in reality, you would be living on a 3-dimensional slice of a much larger space, unaware that directions existed you could never access. Physicists call this the brain world scenario, short for membrane world. In this model, all the matter and energy you have ever encountered exists on a 3-dimensional brain floating in a higher dimensional space called the bulk. You cannot step off the brain, any more than a character in a painting could step out of the canvas. But gravity, unlike the other forces, might leak into those extra dimensions. And if gravity leaks away from our three-dimensional slice, that would explain one of the oldest puzzles in physics: why gravity is so much weaker than every other fundamental force. The electromagnetic force holding an electron to the nucleus of an atom is roughly 40 orders of magnitude stronger than the gravitational force acting on that same electron. That means electromagnetism outpowers gravity by a factor of 10,000 trillion. The weakness of gravity has never been fully explained within the standard model, but if gravity spreads out into extra dimensions while the other forces remain confined to three-dimensional space, the mystery resolves itself. Gravity only seems weak because most of it is leaking away into directions you cannot access. CERN is actively testing both possibilities: tiny, curled up extra dimensions, and large inaccessible ones. If extra dimensions exist at a scale the Large Hadron Collider can probe, particles in high-energy collisions would occasionally radiate energy into those dimensions. That energy would appear to vanish from the collision, showing up in detectors as missing energy that cannot be accounted for by any known particle or interaction. Scientists monitor every collision for exactly this signature, watching for events where the total energy going into a collision does not match the total energy coming out in any measurable form. A more dramatic possibility involves the production of gravitons hypothetical particles that carry the gravitational force, the way photons carry electromagnetism. If gravity does leak into extra dimensions, then collisions inside the Large Hadron Collider might occasionally create graviton-like objects that immediately escape into higher dimensional space, carrying energy with them that disappears from our three-dimensional detectors entirely. The pattern of that disappearance would be distinctive, different from other sources of missing energy, identifiable through the specific way the remaining debris spreads out after the collision. No confirmed detection of extra dimensions has emerged from any search so far, but each experimental run establishes tighter limits. If extra dimensions exist at scales the machine can reach, they must be curled smaller than a certain size, or accessible only through interactions weaker than a certain strength. Every year of operation narrows the possibilities. The connection between extra dimensions and the anomalies emerging from CERN is theoretical but mathematically solid. Several of the models that predict Z-prime bosons or leptoquarks, the particles that could explain the beauty quark deviations and the muon's incorrect magnetic moment, naturally incorporate extra dimensions as part of their structure. The new particle causing the lepton universality violation might not be a simple addition to the standard model. It might be a shadow cast by physics happening in a higher dimensional space, a residue of interactions taking place in directions perpendicular to everything you have ever known. Consider what that would mean if confirmed. An extra dimension is not a small addition to our understanding of reality. It is an entire new direction of existence, a place particles could travel that is perpendicular to length, width, height, and time. If evidence for such a direction appeared in the data streaming out of CERN's detectors, it would mean that the universe you inhabit is not the universe itself, it is a cross-section, a slice, a membrane stretched through a higher dimensional space that your senses cannot access. You would be floating, unknowingly, in that larger space, and there would be forces operating in the dimensions you cannot reach, forces that occasionally push through into your slice, nudging particles in ways your three-dimensional physics can measure but not fully explain. The anomalies at CERN would not be signs that the standard model is wrong. They would be signs that the standard model describes only the physics visible from your particular vantage point, trapped on a three-dimensional surface in a higher dimensional reality. String theory goes further. It suggests that every particle you think of as fundamental, every electron, every quark, every photon, is actually a tiny, vibrating loop of energy in the higher dimensional space. Different vibration patterns produce different particles, the way different vibrations of a guitar string produce different musical notes. The rich complexity of matter and energy would emerge from the simple geometry of strings moving through dimensions you cannot point toward. Testing these ideas requires machines capable of probing the fundamental structure of space itself. The Large Hadron Collider has pushed closer to that boundary than any previous experiment, but it may not be powerful enough to reach the energies where extra dimensions become clearly visible. That would require something larger, more powerful, capable of collisions that recreate not just the first moment after the Big Bang, but the even more extreme conditions when the dimensions themselves took their current shape. Such a machine has already been designed. Its construction would require political decisions, international cooperation, and an investment measured in decades and tens of billions of dollars. But it would possess the power to answer not just whether extra dimensions exist, but whether the anomalies pointing toward them represent the edge of a discovery that would change the human understanding of space itself. While the Large Hadron Collider is still running, while the anomalies are still building in its data, teams of engineers and physicists scattered across the world are already designing something that would dwarf it entirely. They call it the Future Circular Collider. If it is ever built, it would be the largest machine in human history. Picture a tunnel stretching 60 miles around. The current Large Hadron Collider tunnel is 17 miles in circumference, already large enough to encircle a major city. The new tunnel would be so vast it could swallow the entire current machine and still have room for two more just like it. It would burrow through bedrock at depths reaching 800 feet underground, threading beneath the French countryside under Lake Geneva, through the foundations of mountains, connecting to itself in a perfect circle larger than any human construction project ever attempted. The technical specifications read like science fiction. Inside that tunnel, particles would be accelerated to energies roughly 10 times higher than anything the current collider can achieve. At those energies, exotic particles that the Large Hadron Collider can produce only rarely would appear routinely, in large enough numbers to study with the statistical precision that turns hints into discoveries. Higgs bosons would be generated by the millions instead of thousands, allowing measurements of the Higgs field with a level of detail that could reveal whether the standard model's description of it is complete, or whether subtle deviations exist at that point toward new physics. Any particle with a mass below several tens of thousands of electron volts would be within reach. If the Z prime boson causing the lepton universality violation exists anywhere in the mass range most theorists expect, the future circular collider would produce it in such quantities that its properties could be mapped completely. If leptoquarks exist, the machine would either find them definitively or rule them out across the entire accessible energy range. If supersymmetric particles, the hypothetical partners predicted by one of the most elegant extensions to the standard model, exist anywhere below the machine's maximum energy, they would show up clearly in the data. The W boson mass controversy that shook the physics community would be settled within the first few years of operation. The machine is designed to function as a precision factory for W bosons, producing them at carefully controlled energies and measuring their properties with an accuracy 10 times better than any existing result. Whatever systematic uncertainties might explain the current discrepancy between theory and measurement would be eliminated through sheer statistical power and improved experimental design. But designing the machine is one thing. Building it is another entirely, and building it requires decisions that will be made not by physicists in laboratories, but by politicians in rooms where the language spoken is budgets and national priorities and public accountability. The estimated cost ranges between $15 and $20 billion, spread across multiple decades. For perspective, that is roughly twice the cost of the James Webb Space Telescope, and comparable to the total expense of putting the International Space Station in orbit. It would be funded by the same consortium of European nations that currently supports CERN, but an investment this large would require approval at the highest levels of government. Finance ministers would need to explain to their constituents why particle physics deserves resources that could otherwise build hospitals, fund climate research, or reduce national debt. The political timeline is just as challenging as the financial one. Planning and approval for a project of this scale must begin years, sometimes decades, before construction can start. Site surveys, environmental impact studies, international agreements, technological development, all of this groundwork takes time. If the future circular collider is ever to exist, the commitment to build it must be made soon, while physicists are still working to understand what the current machine has already found. CERN submitted the conceptual design report for the project in 2019. An international panel of experts reviewed both the scientific justification and the technical feasibility. Their conclusion was that the project represents a compelling next step for fundamental physics, technically achievable with current or near-future technology, scientifically justified by the open questions the standard model cannot answer. The European Strategy for Particle Physics, updated in 2020, formally identified the future circular collider as the highest priority for the long-term future of European research in this field. But formal endorsement by the scientific community and actual political commitment to fund construction are different stages of a complex process that involves many more voices than just physicists. Some member nations have already signalled that continued investment at these levels requires demonstrated progress toward major discoveries. The anomalies emerging from the current machine provide exactly the kind of compelling scientific motivation needed to justify the next step. But the anomalies are not yet discoveries. They are hints, patterns, deviations that refuse to disappear, but have not yet crossed the threshold of certainty that would make them impossible to dismiss. If the future circular collider receives approval and funding commitments on the current proposed timeline, construction could begin in the early 2030s. The first phase, an electron-positron collider using lighter particles that are easier to control precisely, would be completed in the late 2040s. The second phase, using protons at the full design energy, would follow in the 2050s or 2060s. That timeline means some of the physicists currently working to understand the beauty quark anomaly, the muon magnetic moment discrepancy, and the W boson mass controversy will not live to see the results from the machine designed to answer their questions. Science at this level operates on generational timescales, with each cohort of researchers building tools for the next. The machine would address more than just the current anomalies. It would probe the structure of the Higgs field with enough precision to detect whether the standard model's description is complete, or whether additional fields exist that modify its behavior in ways too subtle for current instruments to measure. It would search for evidence of extra dimensions by looking for the gravitons or other exotic particles that higher dimensional theories predict should be produced at accessible energies. It would investigate the matter-antimatter asymmetry by creating conditions where CP violation effects might be amplified enough to explain why the universe contains matter at all. Perhaps most significantly, it would serve as a direct test of whether the standard model represents a complete description of particle physics, or whether it is simply the low-energy approximation of something larger. At the energies the future circular collider could reach, any new physics lurking just beyond the standard model's boundaries would either reveal itself clearly or demonstrate that those boundaries extend much further than current experiments can probe. The scientific case is strong. The technical challenges are understood and solvable. The international framework for cooperation already exists. What remains is the political decision whether humanity, in the middle of the 21st century, will choose to build a machine capable of answering some of the deepest questions about the nature of reality itself. That decision will determine whether the whispers emerging from the current machine's data, the subtle deviations, the persistent anomalies, the patterns that refuse to fit the standard model's predictions, are followed by the definitive answers they seem to promise, or whether those questions remain unanswered for another generation, waiting for a future that chooses to prioritize understanding the universe at its most fundamental level. The machine beneath the ground continues running. The data continues accumulating, and in the numbers streaming out of those detectors, something is still pressing against the walls of the known universe, waiting to be understood. Listen to the silence. 300 feet below the ground, in a tunnel stretching 17 miles through the darkness beneath Switzerland and France, protons are moving in perfect circles at nearly the speed of light. 40 million collisions happen every second. Detectors larger than cathedrals record each one with precision beyond human comprehension. And in all that noise, in all that data, in all those trillions upon trillions of measurements, there is a silence. The silence is not the absence of discovery. It is the presence of something the equations have no name for. Every anomaly we have explored together, every beauty quark that decayed the wrong way, every muon that spun too fast, every W boson that weighed too much is not a failure of science. It is science working exactly as it was designed to work. Science is not a collection of facts carved in stone. It is a method for pressing human hands against the walls of the unknown universe and learning the shape of what lies beyond through touch alone. The standard model was never meant to be the final answer. It was meant to be a map, drawn carefully from 50 years of exploration, accurate enough to guide travellers, but humble enough to acknowledge its own edges. Every physicist who helped build that map knew it was incomplete. They could see the blank spaces marked with question marks. Dark matter, dark energy, the matter-antimatter asymmetry, gravity at quantum scales. They built the map anyway, because maps do not need to show everything to be useful. They only need to show enough to help you take the next step forward. The anomalies are not tears in the map. They are the feeling of solid ground just beyond its current borders. Consider what has actually happened. For the first time in human history, scientists have built machines sensitive enough to detect deviations so small they would have been invisible to every previous generation of instruments. They have measured the magnetic moment of a single type of particle to more decimal places than existed in mathematics when the first maps of the atomic nucleus were being drawn. They have counted hundreds of millions of particle decays and found patterns so subtle they exist only in the language of statistics. in numbers that shift by fractions of a percent from what the theory predicted. This is not the story of science going wrong. It is the story of science finally becoming precise enough to see what was always there. The universe has been whispering for 50 years. The instruments were not quiet enough to hear it. Now they are. And what the universe is whispering is neither terrifying nor comforting. It is simply true. The standard model describes the majority of reality with extraordinary accuracy, but not all of it. Something exists beyond its boundaries, not something supernatural or mystical or beyond the reach of human understanding. Something natural, measurable, governed by laws that can be discovered and written down in the same mathematical language used to describe everything else. The beauty quark knows something. The muon knows something. The W boson knows something. And that knowledge is not secret. It is not hidden. It is written clearly in the data streaming out of CERN's detectors every single day. Scientists are learning to read that language, one careful measurement at a time. The process feels slow because the signals are faint. But the process itself is extraordinary. Human beings, walking around on the surface of a small planet orbiting an ordinary star, have built machines capable of recreating the first moment after the universe began. They have learned to listen to particles that live for less than a trillionth of a second and understand the stories those particles tell about the forces that shaped them. They have measured the weight of objects too small to see and found those measurements precise enough to detect influences so subtle they might have come from dimensions of space human intuition cannot access. This is not a crisis. It is the most profound success in the history of human understanding. The anomalies point towards something specific, not a vague sense that the current picture is incomplete, but concrete evidence that additional particles or forces or dimensions exist just beyond the current map's edges. The theoretical candidates, Z-prime bosons, leptquarks, sterile neutrinos, extra dimensions are not desperate guesses. They are mathematical structures built to explain precisely what the data shows, with predictions that can be tested, confirmed, or ruled out by the machines currently running and the larger machines being designed for the future. Science is not broken by the discovery that its current best theory is incomplete. Science is energized by it. The future circular collider, if built, will either confirm the new physics the anomalies are pointing toward, or demonstrate that the effects arise from something even more fundamental, requiring tools that stretch the boundaries of what 21st century technology can achieve. Either outcome represents progress. Either outcome expands human knowledge about the structure of reality itself. But the real discovery has already happened. The discovery that the universe still has secrets to reveal, that the map is not finished, that there is still territory to explore. The Large Hadron Collider continues running in its tunnel beneath the Earth. Protons continue circling, collisions continue happening. Data continues accumulating, and in that data, something continues pressing back against the instruments designed to measure it, leaving fingerprints that grow clearer with each passing month. The scientists working with that data come to work each morning knowing they may be the first humans to see evidence of a new force, a new particle, a new dimension of space. They may be the ones to finally understand why the universe contains matter instead of empty light. They may be the ones to identify the invisible substance holding galaxies together, or to glimpse the mathematical structure underlying everything that exists. Or they may simply add one more precise measurement to the growing body of evidence that something extraordinary is waiting to be understood. The silence beneath the ground is not empty, It is full of possibilities, full of questions that have answers, even if those answers require larger machines and longer timescales to discover. Full of the patient work of understanding, one careful observation at a time, the universe that gave rise to consciousness capable of studying itself. You are part of that universe, made of atoms forged in the cores of stars that lived and died billions of years before the Earth formed, assembled from elements that have travelled across vast distances of space and time to become temporarily organised as the complex, thinking, feeling system that is you. The same forces that govern the particles colliding beneath Switzerland govern the calcium in your bones, the iron in your blood, the carbon in every cell of your body. You are not separate from the physics being explored in those underground chambers. You are a conscious expression of it. Rest now in that connection. Let the gentle rhythm of your breath remind you that the universe that seems so vast and impersonal has somehow arranged itself through processes still being discovered to include spaces for curiosity, for wonder, for the quiet satisfaction of understanding something true. The machines will continue running through the night. The data will continue flowing. The universe will continue revealing itself, one measurement at a time, to the conscious parts of itself, patient enough to listen. Close your eyes. Let the steady rhythm of your heart match the ancient pulse of stars. Feel the quiet comfort of existing in a universe where questions have answers, where mysteries invite exploration rather than despair, where the edges of human knowledge are not walls, but doorways opening onto territories still unmapped, still waiting to welcome the next careful step forward into the light. The universe whispers its secrets to those who know how to listen. In underground chambers and orbiting observatories, in equations and experiments, in the patient accumulation of knowledge across generations, humanity continues its longest conversation with reality itself. Each discovery reveals not an ending, but a beginning. Each answer births new questions, more elegant and profound than the ones before. The beauty quarks and muons and W bosons have told their stories. Somewhere in the data, other stories are waiting. The universe is vast beyond imagination, ancient beyond comprehension, and filled with wonders we have barely begun to understand. Rest easy in the knowledge that tomorrow will bring new questions, new tools to answer them, and new reasons to marvel at the extraordinary fact that consciousness exists at all. Here, in this particular arrangement of atoms and energy and time capable of wonder. Sweet dreams await.